Good day, sir. This is our report on probability theory, the law of large numbers. For the introduction, in probability theory, the law of large numbers is a theorem that describes the result of performing the same experiment a large number of times. According to the law, the average of the results obtained from a large number of trials should be close to the expected value and tends to become closer to the expected value as more trials are performed. The LLN, or the law of large numbers, is important because it guarantees stable long-term results for the averages of some random events. For example, while a casino may lose money in a single spin of the roulette wheel, its earnings will tend towards a predictable percentage over a large number of spins. Any winning streak by a player will eventually be overcome by the parameters of the game. Importantly, the law applies, as the name indicates, only when a large number of observations are considered. There is no principle that a small number of observations will coincide with the expected value or that a streak of one value will immediately be balanced by the others. The LLN only applies to the average. Therefore, while the limit of the summation of capital X sub I all over n, as I starts from 1 and goes to n, as n approaches to positive infinity, is equal to the sample mean, or x bar. Other formulas that look similar are not verified, such as the raw deviation from theoretical results, or the summation of xi, as I starts from 1 and goes to n, is n times x bar, where kaning capital X sub I, this is value ni siya sa in an experiment, or this is the random variable. Not only does it not converge towards 0 as n increases, but intends to increase in absolute value as n increases. Here we have an example. A single roll of a fair six-sided die produces one of the numbers 1, 2, 3, 4, 5, or 6, each with equal probability. Therefore, the expected value of the average of the rolls is, i-add na to ang mga possible nga makuha na to from the rolling of one six-sided die. We have 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we divide it by the total number of observations that we could collect. Divide it by 6, and then we get our expected value, or in this case, it is the arithmetic mean. According to the law of large numbers, if a large number of six-sided dice are rolled, the average of their values, sometimes called the sample mean, will approach 3.5, with the precision increasing as more dice are rolled. We have two different versions of the law of large numbers. They are called the strong law of the large numbers, which is also called Kolmogorov's law, and the weak law of large numbers. Today we will discuss the strong law of large numbers. The strong law of large numbers, also called Kolmogorov's law, states that the sample average converges almost surely to the expected value, or in notation, x sub n bar approaches almost surely or converges to the expected value, or the sample mean. We have mu when n tends to infinity. That is, the probability that the limit of x sub n bar as n approaches infinity is equal to mu is equal to 1. What this means is that the probability that as the number of trials n goes to infinity, the average of the observations converges to the expected value is equal to 1, or 1 meaning it is 100% certain that it will happen, na the averages sa mga observations, if we do the experiment again and again and again, right, theoretically towards infinity, an infinite number of times, ang makuha na to nga average will converge to the expected value that we got by by adding all the possible observations, dividing it by the number of observations. So the modern proof of the strong law is more complex than that of the weak law and relies on passing to an appropriate subsequence. The strong law of large numbers can itself be seen as a special case of the pointwise ergodic theorem. This view justifies the intuitive interpretation of the expected value for Lebesgue integration only of a random variable when sampled repeatedly as the long-term average. Law 3 is called the strong law because random variables which converge strongly or almost surely are guaranteed to converge weakly in probability. However, the weak law is known to hold in certain conditions where the strong law does not hold, and then the convergence is only weak in probability. The strong law applies to independent, identically distributed random variables having an expected value, like the weak law. This was proved by Kolmogorov in 1930. It can also apply in other cases. Kolmogorov also showed in 1933 that if the variables are independent and identically distributed, then for the average to converge almost surely on something, this can be considered another statement of the strong law. It is necessary that they have an expected value, and then of course the average will converge almost surely on the expected value. So in the case of a six-sided die, the expected value is 3.5. If the summands are independent but not identically distributed, then x sub n bar minus the expected value of x sub n bar, or expected value sa average of observations denoted by n, almost surely converges to 0, provided that each x sub k has a finite second moment, or the second moment is also called the variance, and the summation of 1 over k squared times the variance of each x sub k as k approaches to 1, k starts from 1 and goes to infinity, is less than infinity. This statement is known as Kolmogorov's strong law. And that is it for my part, and Agan Ivankith and Agan Gleiselmay will discuss the central limit theorem.